Hello everyone who's watching. My name is Ijaz Sayed and I'm taking ME56900 Mechanical Behavior of Materials this fall 2022, and my presentation topic is effective annealing treatment and mechanical properties of 811 aluminum by cryogenic rolling. So let's get started. The main objective of this study and experimentation is to improve the mechanical properties of our specimen, which is 811 aluminum alloy, and we are doing that by roll casting and annealing. So the annealing of aluminum in 6 different cryogenically phases not only affects it actually affects in the grain strengthening of individual aluminum atoms. This in turn uh, improves not only its tensile strength but also the different mechanical properties such as yield strength, hardness, and the thermal stability of the material. This is very this has a very great impact on the versatility and general usage of aluminum. Moving on, acknowledgement. This presentation is based on the study titled with the same name, Effects of Annealing Treatment on Mechanical Properties of the Aluminum Alloy 8011 after cryogenic rolling. This study was conducted by Junjun Kui and team. For anyone interested on the study, I have mentioned the link below. You can use it. Moving on, introduction and background. As we know that aluminum is extremely versatile metal, and in the past years, its use has increased manifold. Its presence can be felt in myriad of industries such as construction, packaging, transportation, industry, electronic and mechanical manufacturing, etc., etc. This is due to the low density, optimal plasticity and strength, and effortless surface processing of the metal. Moreover, it's very easy to process in different shapes. We have all seen aluminum plates, aluminum foils, etc. We have also seen bars and pipes made of aluminum because it's very malleable and extremely uh, easy to manufacture metal. It's actually the second most used metal after steel and the counterparts of iron. Uh, yeah, so that's about our introduction and background. Moving on, uh, annealing and its effects. Why we are using annealing to improve the mechanical properties of aluminum. There are several different methods to actually improve the mechanical properties, such as laminated rolling bonding, equal channel angular pressing technology, high pressure torsion, reciprocating extrusion, etc. However, these methods make microstructure of aluminum alloys in the recovery phase. And in order to improve the mechanical properties, the ultra fine grain can be obtained by rolling at the temperature of liquid nitrogen before heating quickly. Various studies has implicitly shown us that the deep cryogenic rolling can effectively inhibit the occurrence of dynamic recovery and has obvious advantages in increasing the strength and grain refinement. So annealing treatment of rolled aluminum can not only eliminate the work hardening and stress concentration, but it also improves the thermodynamic ability of the metal, which is a great advantage. So the experimentation is done in 6 phases. Obviously, we're using the AA aluminum 8011 specimen here. It will be rolled in 6 phases, and the reduction ratio is 30% for each rolling pass, and the total reduction ratio is 85%. Firstly, the aluminum plate is clamped by the clip, as shown here in the first figure. It is cooled for 1 hour in the liquid nitrogen drum. After cooling though, the aluminum plate will be rolled quickly in accordance with the rolling direction. For the next rolling pass, the aluminum plate will be cooled for half an hour in the liquid nitrogen drum and rotated for 180 degrees to prevent warping. During the deep cryogenic roll process, aluminum produces large strain and internal energy, so microstructure in thermodynamics is unstable and has trend to transform stable state. The annealing treatment can improve the thermodynamic uh, stability of the cryogenic rolled aluminum and can make grain refined and uniform. So after cryogenic rolling of 6 passes, cryogenic roll of aluminum is done at myriads of different temperatures, which is mentioned here. It's done at 100 degrees, 120, 140, 160, 180, etc., etc., 260, 280, and for about an hour. According to optimized temperature, the sample holding is for 10 to can between 10 minutes to 80 minutes for aluminum. So this concludes the experimentation part. And what are the effects of experimentation? A couple of different tests were carried out to actually measure what was different before the rolling and annealing and after rolling and annealing on the aluminum. So these were actually done to gauge the tensile test to gauge the tensile strength and the hardness. So the tensile strength is carried out by the CMT5105 microcomputer controlled electronic universal testing machine. The tensile specimen is shown in figure 2. The sample was snapped with the tensile rate of 3 mm per minute, and tensile strength, yield strength, elongation, and contraction were measured. The Vickers hardness of rolled cast and deep cryogenic rolled and annealed aluminum were measured on sample film of 10 mm after polishing. So what were the results? The results on the microscopic level are mentioned here with figures. The grain is elongated along the rolling direction and grain boundary in discontinuity. This is before annealing. Many corrosion pits exist in the microstructure due to the existence of ferrous in aluminum. Ferrous here, which is the main element of iron, is a harmful impurity which has influence in corrosion resistance. The figure 3b here is the metallographic structure of aluminum after rolling for 6 passes. Compared with the roll cast state, the grain is more elongated along with the rolling direction, and with the increased deformation, the fiber microstructure is fine and no recrystallization occurs here. The tensile strength of aluminum has increased from 134 megapascals to 235 megapascals. The yield strength has increased from 91 megapascals to 189 megapascals, and the hardness from 47 HV to 79.6 HV. These values were about two times the roll cast state of aluminum. The figure 4 shows the hardness of aluminum annealed at different temperatures after cryogenic rolling. It can be found that the hardness values decreases only slowly, annealing at 100 to 200 degrees Celsius. However, the hardness decreases obviously with the increasing of annealing temperature to 220 degrees Celsius. After deep cryogenic rolling for 6 passes, there are defects and high dislocation density in the interior of aluminum. Conclusion: the total reduction ratio of deep cryogenic rolled aluminum is 85%, and the roll sheet has no warping and no fission. The final microstructure of deep cryogenic rolled aluminum A211 is fibrous and uniform. After deep cryogenic rolling, the tensile strength, yield strength, and hardness of aluminum all were improved. The hardness of aluminum after deep cryogenic rolling is decreased with the increase of annealing time and temperature. So hardness has an inverse relationship with annealing temperatures. The optimum annealing temperature for aluminum is 220 degrees Celsius and holding time is 40 minutes. The tensile strength is 202 megapascals, which is about 1.5 times the fuel cost of AA8011. The thermal stability of deep cryogenic roll is better. So these are the references for the study, and I thank you very much for watching. Bye.